Well, welcome everyone to this afternoon's webinar. My name's Carl Larsen from RMCG. This is the third webinar in a national series of 4. Today we're focusing on robotics, intelligent systems and automation, so a bit of a future focus. We've got a number of really great guest presenters lined up for you today to take us through the topic, and it's being delivered under the National Vegetable Extension Network, or VegNET as you might know it. So just quickly a little bit about VegNET itself. It's a industry development project set up and funded through Hort Innovation, and there's 10 regional delivery partners. RMCG is the delivery partner in Vic and Tassie, but right around the country there are now industry development officers or field officers in each of the main vegetable growing regions to help right through from production-based issues and R&D, right through the value chain, post-harvest business management, but really with the aim of getting that levy-funded research out onto farms. So today's session, we've joined by Justin Clark from the University of Sydney, who's going to provide us with, I guess, the researcher perspective with some of the great work that team's doing on the Ripper robot and Ladybird, which you might have heard a little bit about and they're interested in knowing more. We've also got David Carey from the Department of Ag and Fisheries in Queensland, who's going to be talking to us about some vision system and sensor networks projects that they're currently doing for Hort Innovation. And Tim Neal from DataFarming will be kind of providing us that practical and agronomist perspective at the end to really say, well, how's this stuff being used now and where does it plug in when you put the boots into the paddock? So what's really useful for us to understand is just who's on the line. So what I might do now is just launch a quick poll, and you'd see up on the screen there just asking how much experience you have in agricultural robotics and broader automation. If you could select one of the options there, just lots, a bit, not much, or none, keen to know more, that just gives us an idea of who's on the line. I can see about 60 or 70% of us have clicked in an option, so thanks for that. And getting up to 90% now, so I'll just close that one and share the results back with you. As you can see, we've got a few in that upper tier, quite a strong cohort with a bit and not much, and a third with none but keen to know more. So that's really good. Thanks for sharing your insight there. That just gives us a bit of an idea of where to pitch some of the information, particularly some of the curly acronyms that we can come up against in this area. So I'd like to now hand over to Justin, who's going to take us through the first part of the discussion and a little bit about, just go to webinar control panel on the side. You'll see there's a section for questions. Feel free to type those in at any time. They'll come directly through to me and we can put them to the presenters, one or all, at any time, just to make it a bit more interactive and less kind of one way. I know we've got about 50 people joining us from around the country, so hopefully a really good opportunity to get some of those questions going. So Justin, I'm just going to hand over the mouse and present it to you. Just a minute, and that should be coming through to you now.
Yep.
Fantastic, over to you.
All right, thanks Carl. Thanks for joining us everyone. Today I'll be talking about the Ripper and Ladybird projects that we've been working on here at the Australian Centre for Field Robotics. We're based out of the University of Sydney. So as part of these projects, we're looking at autonomous systems that can run on leafy vegetable crops. So that's lettuce, broccoli, cauliflower, and baby spinach are our sort of core focus. And we've got 2 robots, Ripper and Ladybird. One is focused more on the research side, that's Ladybird. And as you can see on the screen here, that's the top robot you can see there. And that one's about collecting a lot of sensor data, seeing what we can do with that sensor data, whether that's make predictions about yield, predictions about plant health, and then from that we can then develop decision support systems. That then feeds through to our second robot, Ripper, which is the one lower down on the screen. And that's part of taking that decision support system and sensor collection data and then applying that on an autonomous robot that drives up and down the rows of crops and interacts with them directly. So that might be spraying, it might be doing mapping and so forth. And that's all about taking the research and then all the way through to an operational prototype level, which would then be passed on to commercial partners to take the project further. So to give you a bit of an overview of the Ladybird robot, so as I said, that's the research-focused platform. So with this one, it's got a whole plethora of sensors. So that might be hyperspectral sensors. What they are is that our eyes can see 3 bands of light. The hyperspectral camera can see over 400 bands of different wavelengths. So we can look at the crop and try to find out, is there things that we can't see that it can see that show a plant might be not as healthy, a plant might be struggling due to water stress, due to lack of nitrogen, or all sorts of things. And so it's about collecting that data on the plants and seeing if we can find if the sensors can pick up something that we don't already know that we can see. We've also got stereo imaging sensors. So what that might mean is we can create a 3D model of the plant as we go over the top. The way this robot works, it's an autonomous platform that's solar powered. So that means we can set it up on a farm, we can teach it the rows of crop. It'll then drive up and down each row, scanning the data. So when it does this, we can then map the plants based on a GPS location. So up on the screen, you've seen here an image of a trial plot that this robot runs on. So it's got a broccoli and cauliflower crop that it's sort of scanning on a weekly basis. It then knows, it can keep track of each plant and track its health and how that shows up in the sensor data. We also then use ground truthing. So that means going out and taking physical measurements of the plants and then comparing that to the data so that we can see, is the sensor telling us something? Is the ground truth data telling us something? Do those match up? Does that mean that we can then use that sensor data to give us useful information about the crop? As I mentioned, once we collect that data and we can sort of draw those links between sensor readings and actual physical attributes of the plant, we can then develop things like yield estimation, crop growth models, and things like that. So from here you can see we've detected each crop. As we've detected it, we can create a 3D image of it. As we do that image, we can then sort of get a volumetric estimate of the plant size. We've also done that with taking a top-down view. So in this data here, you can see sort of the reasonable correlation between the predicted fresh weights. That would be taking that top-down view and measuring what the plant looks like, what the size looks like from above, and does that actually relate to the 3D fresh mass of the crop. So it's all this sort of things we're investigating to see how can we use cameras and sophisticated sensors to look at the crop and give us information in real world that we can then use and apply on the farm and to give to growers. Ripper then takes it to the next stage. So we have done on-farm trials, about 15 or so in the past 2 years, up and down the east coast of Australia. So on those trials, Ripper robot goes out and it uses much simpler sensors than Ladybird, but tries to then apply what we've learned from Ladybird and then also interact with the crop directly. So it's, again, an autonomous solar-powered robot. So that means we can teach it to drive up and down the rows of crop by itself, and it can do that sort of 24 hours a day. And as it does that, it's taking images of every plant as it goes over, and then we can get information back about those plants. Another focus is also weed management. So it's all about reducing the inputs for farming, using the sensor data we're collecting to then develop these decision support systems that then mean we can optimize how much, say, fertilizer is applied, look at how do we reduce the amount of weeds present, how do we manage those weeds as we go over the top. Recently, we've built a second Ripper that helps us so we can have one in development in the lab and the other one out on site doing field trials. And we're working more and more on developing the learning models using machine learning to identify where the plant is in the images, where the weeds are. And that, again, helps us sort of pinpoint where's a plant, what information about that plant is useful, what can we do, whether that's spray the plant, whether we And then with weeds, whether we spray the weeds with a herbicide, whether we try knock them out with mechanical weeding system. So, as I mentioned, there's decision support systems such as sensors, which is just collecting all the data. We then turn that into like a map of the whole field and how those sensor data varies across the field. And we'll feed that through to crop intelligence. And that's about developing those full decision support systems that then can either feed information to the grower so they can then go out and apply that. So that might mean this area needs attention, need to boost the calcium in the soil in this area or something along those lines. But then with this autonomous system, we're also looking at how do we take it to the next step with the robot. So that means going into crop interaction. So you'd go, okay, we need to spray extra fertilizer in this zone, not so much in that. And so the robot can then drive over and in real time as it's measuring the plant, where maybe make that decision based on size. You can go, okay, the smaller lettuce, you need to give them a boost of fertilizer. The larger lettuce, not so critical. And that's part of what we're trying to do as well, is see, is that sort of a useful use of the robot? Is it actually try to even out crop uniformity and try see if we can get an autonomous system that can do that whole cycle of collect data, make a decision about that data, then act directly with the crop all in real time. Another big area is not just crop health, but it's looking at weed management with the Ripper robot. So we've done both mechanical weeding, so that's detecting where the weed is. A tine drops down and sort of scuffles the weed out of the ground. We've also done spraying of targeting to spray herbicide onto weeds as we're driving over. And we're also looking at foreign object removal. So that would mean, say, prior to harvest, you want to detect, is there any sort of bottle caps, rubbish left behind in the crop, other items you don't want pulled in with the harvest. I mean, that's a particularly big issue for ground cover crops, such as baby spinach. So with that one, we've sort of demonstrated driving over the top with a vacuum that, as it goes, the vacuum drops down and sucks up the items that it detects with the camera system. And so the Ripper robot is quite different to the Ladybird in that it just has, using basic RGB and near-infrared cameras underneath to make all these decisions and detections, whereas the Ladybird is looking at a much wider band of image data. But the idea is, as we learn things on Ladybird, and the research continues with that one, we then hopefully feed that down through to the Ripper and keep developing and making more robust these decision support systems on Ripper and what the different crop interaction mechanisms are. So unfortunately, there was a little video here, but it won't play with the stream, but I'll just talk you through some of the different things Ripper's done. So here you can see an image of it driving up and down the rows of crop down in Victoria. So here it's got the camera's pointing straight down over the crop, collecting data. Here you've got it driving over the top, doing object section removal. So you can see this sort of, in the middle of the image is a vacuum nozzle, and that sort of can pivot left and right and drop down and suck out the objects as it needs to. As I mentioned, on the farm, as it drives over, it's got that camera underneath. It's then taking pictures and then identifying where the crop is in each image, which is in the second image in that flowchart. Once it knows where all the plants are, it can then map the GPS position of those plants, because the robot is using GPS location, so it knows where it is each time it takes a photo. We can then link a plant to a GPS location, and then we can map all the plants across an entire paddock into a graph, and so you could interact with that graph and see areas of interest. So if I jump to the next slide once it loads, on the left you can see an example of a crop map. So in this one you'd see the red areas on the very edge, that's where there was sort of no crops, more soil. So and then towards the bottom of that image, the rows are a bit more yellow compared to the dark green in the center. So the yellower area means there's less plant matter that's been detected. So you might go in that area, there might be some sort of deficiency in the soil or the water or the fertilizing, and so the plants aren't growing as big. That can quickly give you that sort of overall bigger bird's eye view of the whole paddock at once and go, okay, that's an area I want to investigate. You can then hover over a specific area and it'll bring up the images that the robot captured. And so you can sort of inspect in detail. And if you just so decide, you can go, okay, this is the GPS coordinates of that location. I'll then go out and physically check the area out in the paddock. We've done soil sample mapping. So what we've done there is we've driven up and down a couple of rows of crop. We've taken a soil sample every 1 metre, and that's measuring moisture, temperature, and conductivity. And once it's done that, we've mapped that so you can see the variation of those parameters of the soil across the 4 paddocks. So you might go, okay, this area is a bit low in moisture, maybe the irrigation system isn't working as well in that area. And so the idea, these are just small examples of how a system like this can, by itself go up and down, collecting this data, give it to you in a format that you can then understand and take action on. And in the longer term, it might be the robot could then go and take action or give prompts to an irrigation system to make the changes as necessary to try create a more uniform crop, more evenly and optimized distribution of inputs. So whether that's how much labor you need to going out for doing weeding, for harvesting, it might give you a better estimation of how many people you'll need because you'll only be harvesting 20% of your broccoli crop this week, and next week it's the other 60%, another 60% is ready for harvesting. And so this can give you sort of really detailed information, but in a much more digestible manner, and then you can then use that to sort of optimize your operations on farm.
And Justin, just a quick one there on the soil mapping charts that you've got in the bottom left. Could you just indicate, due to the font size, which one's moisture, temperature?
So the one on the left is moisture, then the center one is temperature, and the right one is conductivity.
Great.
Jumping back to some of the research that Ladybird has been carrying out in more recent months. Here is looking at the development of growth models and looking at, can we use a combination of various scientific agriculture indices that are available. Examples of those are like, more common one is NDVI, which is a measure of greenness. And on this slide, you can see probably about 20 or so different indices, and they're all essentially looking at a similar sort of way, but a different way of looking at greenness and plant health and fluorescence of the plant. And so we're looking at, is there ways we can combine one or two of these together to give an indication of the plant health that we sort of haven't been discovered yet? So that's a sort of big area of ongoing research. How they're doing this is, in this example, this is all the same. Each row here is the exact same row, but just analyzed with a different indice. But what we've done is we've varied the water and nitrogen application across that row. So you can see on the left is sort of a high water, low nitrogen, and then it moves to high water, high nitrogen. And so that blown up area sort of shows the change from photofluorescence of the plant. So on the left-hand side, it's, you can see much sort of smaller, less biomass being created. Whereas on the right, where there's a higher level of nitrogen being applied, you can see the indice really showing the plant really being more fluorescent and reflective. So that's sort of a ways of investigating how the sensor data we're capturing with these autonomous platforms can then feed back into information about the plant, and then hopefully develop a decision-making algorithms from that.
And Justin, we've just got a quick question that's come in from Supriya, just asking, for this type of data with the NDVI and other greenness indices, I mean, who are the typical users of that data at the moment, given that this particular piece of work you mentioned is in the research phase with Ladybird?
So I guess it would be, as we develop these, it would then be something that becomes available from the research. So, I mean, these are all the ones listed on this slide are ones typically used already among the scientific community. And so we're looking at other ways that we can combine two or more of them together, and that when used in conjunction, that they can give insights that aren't already available. So I'm not sure that quite answers the question, but I guess the idea is that we're sort of trying to come up with novel ways of identifying indicators of plant health for later use.
Great, thanks.
So again, one of the other things we're looking into is sort of yield prediction and looking at, can we reduce the variability in a crop? So part of this would be collecting weekly snapshots of a plant and then tracking how that plant varies over time, how that plant might change due to different inputs. So if that's varying the input of water, varying the input of fertilizer. Just excuse me a sec. And from that, we can start to build up a plant history that can then inform, as we do that over multiple crop cycles, that can start to inform if there's decision support systems, because you can go, okay, with this input in this region of Australia, we were able to get this sort of result consistently over time. That will then feed through to the yield prediction, which is the bottom half of the slide. And that might be where you go, okay, this plant at week 7, this is where we expect it to be, so we probably don't need to either apply fertilizer or just a minimal amount. Or we go, oh, okay, week 7, this plant is a lot smaller than it should have been. What are ways we've identified that would sort of boost that back up to where it needs to be? I mean, I'm just using fertilizer as an example of what that input might be, but there could be various ways, maybe soil health or different things that you might need to identify as the issue. But it's all about saying, can we sort of, with an autonomous robot, it gives the advantage that you can capture data on every individual plant in a paddock, which is something you can't do if you want to manually go out there. It's just too time consuming. But the robot, it can run constantly, it can collect this data weekly or twice a week on hectares of crop. It can then store all that data. You can then analyze it and give information and a history about the plant and give much better ideas of yield prediction and how to get more uniform crop based on the decisions you can make about it. So again, it's like putting in fertilizer, this one needs more water. And so it's quite a tricky area, but it's something we're sort of digging into a lot with the research, and we'll continue doing trials where we're sort of scanning and spraying crops over the entire crop cycle. We're gearing up for one next month at the University Farm in Camden here in Sydney, and that one will be doing spraying of fertilizer over the crop. So that'll be looking at, okay, can we say use something like the size of a crop to give an indication of which ones are maybe struggling, which ones aren't. If we then apply more fertilizer to the ones that look like they're a bit smaller, will that boost them up? Or maybe it won't. That's one of the things we're trying to look into and see if we can sort of find a result there. And it's also about seeing, can we use a robotic system to sort of close that loop of detection, understanding what's going on, and then actually acting on it in real time. Again, talking about what we're sort of moving on to next. So here you can sort of see this TRL status. What TRL sort of stands for is technology readiness status level, technology readiness level. So here might be really hard to see with the font, but at TRL 7, where a lot of the earlier items we've investigated are at, that means it's sort of a demonstration system and operating in the environment. So that's where we're gone out and demonstrated it on commercial farms across Australia, like I mentioned earlier. So that's talking about the actual autonomous platform. The Viper unit is the spray unit that we use for either herbicide or fertilizer spraying. Weed detection is using the cameras underneath the robot to detect where weeds are present. There's mechanical weeding, again using a similar system, detecting where the weed is, but then dropping down a mechanical time that scuffles the weeds out. Soil mapping, which I showed earlier, and yield and variability maps. That's about the crop mapping stuff I showed earlier, and then foreign object stuff. So all of those are a fairly high technology readiness level. So that's sort of at a stage now where we're looking for, Hort Innovation is looking at talking to commercial partners to see if we can sort of spin off some of these technologies, whether all together or one at a time. But while that's happening, we're investigating new areas such as health and pest of the plant. So looking at, and that's sort of what Ladybird's currently working on now, is scanning it, the crop. Can we identify where pests are? Can we identify in more finer detail the crop health? And then also looking at the individual automated fertilizer dosage. So again, like I was saying, can you work out that this crop needs more than the other one? And since we can apply fertilizer on a per plant rather than a per hectare basis, you can really drill down and just give a really optimized and sort of unique dosage to each plant to try to get them all to the same level of health and size and greenness and ready for harvesting. So that's it from me. Please feel free to ask any more questions if you have any. And yeah.
Fantastic. Thanks for that, Justin. A really good overview of some of those exciting projects with the ground-based robots coming out of Sydney Uni. We've got a couple of questions that have come through, but what I might do in the interest of time is just hand over now to David and see if we can get to those questions later on in the session. If we can't, we'll definitely make sure we follow up afterwards. So David, I'll hand over the screen to you now. That should be coming through to you to bring up your presentation. And just confirming, David, we can view your screen and we can see the title slide up. So over to you. Oh, sorry, David, we've just don't have audio for you. You might be muted.
Yep, now I'm good.
There we go, we've got you.
Okay. Thank you very much, Carl. Appreciate that. Good afternoon, everyone. Just wanted to give you an update today on a Hort Innovations funded project being run by DAF in collaboration with QUT and CSIRO. Vision systems, sensors and sensor networks to manage risk and increase productivity in vegetable production systems. We're doing this in conjunction and with the help of the local grower associations in Queensland, Bowen Gumloo, Lockyer Valley Growers and the Bundaberg Fruit and Vegetable Growers. There's two main components to the work, the rapid yield assessment and the early problem detection, which I'll go into quickly now. The first part of the work, DAF staff are conducting with QUT staff. It's about rapid yield assessment using vision systems. So using inexpensive 2D and 3D sensors, like cameras to we mere mortals, to detect fruit on the crop, and then to take it that little bit further and to try and actually classify size, colour, shape, and colour change in that crop to really refine crop mapping, I suppose. So you can see in the number one slide on your left-hand side, I hope, we've got a capsicum crop there. We've got a couple of things going on. We've got two commercial varieties, both of them set up as double row and single row entities, just to test the accuracy and whether that variation gives us a better result. And you can see one of the QUT researchers walking along there, holding a sensor array at the bottom of his hand, imaging the crop. And at the bottom right-hand corner of that same image, you'll see a little yellow robotic platform with a laptop computer sitting on it. That's got some cameras latched onto that, and that goes along and actually images the crop. Slide 2 is a picture of some capsicum fruit in a protected cropping area at Garoo in North Queensland, because we did some protected cropping work. And that just shows the mature fruit with the label numbers, and I'll explain that later on. On the right-hand side, you can see that's the images from the Gatton crop taken by the sensors on the left. The crop on the left, and you can see that it's quite a difficult issue to see capsicums, particularly green capsicums, in a fully grown capsicum crop in the field. But that little red square you can see is where the camera software has detected that there is a green capsicum hidden amongst the foliage. The next section here just really outlines the fact that this is work done in the protective cropping section in Garoo. Protected cropping was done as well as field cropping. Protected cropping gives you a few advantages. You've got a level flat platform to start with to drive your robotics along. You've got a covered environment. You're dew-free and you haven't got any mud. You can see the fruit that's lined out to the right of the pots, and that fruit is what is used to calibrate the system and help the machine learning so that the computer knows how to classify fruit. And I'll talk to that in a little second. The important thing to realise there is that 50% of the fruit harvested from each plant is used to train the software, and the other 50% is used to test the software. So from a field perspective, hopefully you can see that slide now. On the left-hand side at the top, there's a yellow crate. The QUT researchers have gone through and taken camera images of the crop, the capsicum crop in the field, with a 3D scanner that has depth perception so they can gauge the size of fruit. Then comes the harder work, or the more complicated, well, more labour-intensive work, I suppose. All those fruit have to be picked, and then those fruit have to be graded. So you can see a poor image of a data sheet at the bottom there, which has got fruit numbers 1 to 16 on it. And if you look at the image on the top right of your screen, those capsicums, you can see there's a fruit number 16. So what we do is we go and we harvest all that fruit. We match fruit number 16 with where it was sitting because it was visible where it's sitting on the plant, and then we grade that fruit. So we rate it we measure the height, we measure the width, and we measure the weight, and that's classified as a large green. And that then drives the mathematics to say that an image that size will be a large capsicum. We know it's green because we've got a colour camera on there. So how's that working? And the protected cropping system, here's some early results. Out of the 100 fruit that's visible to the naked eye, the QUT algorithms can identify 80 out of the 100. And then in terms of size grading, you can see that on average it gets 90% of all the fruit correct. It gets 94% of green, 91% of red, and 70% of mixed colour. It grades as mixed colour. Take it to the field where you've got that level of occlusion. You can see in that bottom left-hand slide all the leaves that we need there to stop sunburn in the field. You can see how well that fruit is hidden, but the camera's picking up fruit and also picking up some false images, which we have to train it out of, as opposed to here on the right where you can see in the glass house, fruit's quite visible. So in the field, it's only getting 70 out of 100 fruit, but still overall, the accuracy is 91.5%. We're still waiting to dig into the data. We want to see whether there's any difference in varieties, because the varieties put fruit on different physiological positions on the plant, I suppose. And also we're looking at single versus double rows. So a single row where you get more light interception through the crop, we should get a better result. We're still digging into that data. The next part of the work we're doing, and this is with CSIRO as our research partner, is looking at hyperspectral imaging. And we've chosen to work with tomato spotted wilt virus. And you can see in the bottom left-hand slide, you can see a pot trial that's set up there, a replicated trial with a number of plants. The reason we use tomato spotted wilt virus is what you're trying to do is you're looking at the change in leaf reflectance or light reflectance, wavelength reflectance actually off the leaf. So you need to have diseased and non-diseased plants, or affected and non-affected plants, growing in the same environment under the same light conditions and the same humidity conditions, because otherwise you'll get variations in your leaf texture, leaf colour. So that's got to be uniform. So we chose tomato spotted wilt virus because it can be mechanically inoculated into the plant, and you'll know that you can have an inoculated plant sitting beside a plant that wasn't inoculated, and the disease won't or the virus won't transfer from the inoculated to the non-inoculated plant. And you can see here, 3/4 of the way through the trial, that the wilt virus in this particular trial has actually stunted that plant, and possibly this plant, whereas here's a healthy plant and here's another healthy plant. The process was then to take those leaves off, take a leaf off a plant after a virologist had in the glass house had looked at the leaves and assessed them for virus presence and the level of virus. A leaf was then taken, it was identified with a number, sent down to the camera crew downstairs, where CSIRO and their technicians did a lot of scanning using this bespoke camera rig that they've designed that uses very infrared, a hyperspectral wavelength. So it's looking at very near infrared camera that's running from 400 to 1,000 nanometers, and then a shortwave infrared camera, which produces a wavelength, which I'll talk to later on. And then the aim of the work is to see whether that wavelength can decipher infected from non-infected plants. How does it do that? You're all aware of NDVI. I'm not going to go into it too much because Tim's going to talk to that later on, I suspect. Here's an NVI image of a paddock. Basically, green's very healthy, yellow and orange are less healthy. And that's determined between about 0.4 nanometers and about 1.2 nanometer wavelength, so in this zone. And it's comparing reflectance within that zone. What we're doing is and this is red, green, blue, so that's color spectrum that a camera can take and you can see. This is the hyperspectral image that we're working in, or the reflectance wavelength, which goes from 0.4 nanometers all the way up to 2.5, so it's non-visible. So the question is, can we use that reflectance of light, electromagnetic radiation from the leaf to determine if there's a disease present? If you look at the schematic here, just to try and explain that a little bit, NDVI works in about this wavelength here and looks at the differences in reflectance. What we're doing is we're actually trying, I've lost my screen, we're actually trying to find a signature wavelength somewhere in that spectrum between 0.4 and 2.5 nanometers that gives an indication, an early indication of a disease in a plant. So this imagery is actually of the different leaves in a forest, but if you pretend that was a healthy leaf and that was a leaf that had rust or tomato spotted wilt virus or powdery mildew in lettuce, you can see that there's a difference in the spectrum. I've got a bit of lag here. At this point, whereas if you look close to the axis, down this end of the ski, you can see that there's not much difference there, so you couldn't really pick any difference. But if you look way up here at the high end of this light reflectance spectrum, it could be we're looking for something where this is the reflectance from a damaged or tomato spotted virus infected leaf, and the top band is where a healthy leaf would reflect. So it's all about leaf reflectance, and there's a range of information there you can follow up. The next part of the work, we moved on from individual leaf scanning, which hadn't been done in capsicums or many vegetables all to date. And then we've moved on now in the last 2 trials, we've done whole pot scanning. Siro have made some real headway and built a whole plant scanning rig. And this is just to really show you how much work goes on in the background. So this is a normal camera photograph of a pot that's being scanned, that's gone down to the hyperspectral camera. As well as that red, green, blue photograph, there's also a wavelength image or wavelength reflectance that overlays all that imagery. You can see the little blue squares. That's where the virologists or the experts have actually gone and said, at that point on that leaf, there is a disease, obvious, and they've named a number of them. And in this particular case, they've said, oh, that's mosaic, and it's contained in this area. These plants were scanned 3 times a week from about 5 days after inoculation for about 5 or 6 weeks. So there's a lot of data to go through. And at the end of the day, this imagery is actually used to look at the reflectance, the difference between a known damaged or infected area with a known disease or virus and a normal healthy leaf reflectance on the outside, to try and drive that computer to learn, train it to learn to look for damaged leaf material early before the human eye can see it. We've done a lot of industry engagement and communication throughout this process. The idea is to produce fit-for-purpose technology for industry. We have annual regional forums in Bowen, Bundaberg and Gatton. We're working in close collaboration with Bowen Gumlu Growers Association, Bundy Fruit and Veggie Growers and the Lochte Valley Growers Association. We put out 2 project newsletters a year. We also have grower levy payer partners who are growers sitting in each of those Bundaberg, Bowen and Gatton areas who are providing feedback on a regular basis to our project work. Outcomes to date. It's really a cutting edge area, this, because there's very little data in terms of hyperspectral imagery around, particularly in horticulture world. There's a little bit in broadacre world, but not much at all in horticulture world, so it's a bit of a first. We've developed, but in the capsicum rapid yield assessment, we've developed fruit classification algorithms, and we've tested them in commercial varieties in the field. We've identified appropriate cameras, we've identified appropriate sensors, we've field tested them. We've challenged the technology in the real world environment. Quite interesting, when we were doing the imaging trial runs in the capsicums in the field in Gatton, It was best to run in low light conditions, so you didn't get a lot of reflectance, and you got a better imagery, which leads to the fact that you could actually run that. You'd be actually best running that technology at night when you're not on the farm anyway, and you could actually develop feedback and develop yield maps when ready for the next day. There's a large labour need to classify and do all the background wording to train the system. It's a bit like an iceberg. You see the output at the end, but under the water, all this background harvesting, yield and training goes on. There's masses of data to try and train the computer and train the set the mathematics up in the background to derive a sensible outcome from the photograph or image that you've taken. The potential for this is like a yield harvest module. If any of you are aware of Harvey, the robotic capsicum harvester, you can Google that if you're not. That's an automated robotic platform picking system. Now that we've developed a yield assessment system for that, not only can Harvey pick capsicums, but he can go through and he can classify. So he can pick, or she, it can pick large red capsicums, large green capsicums. It can pick breaking fruit capsicums, or it can just go through and tell you that if you are trying to pick greens, you're starting to see some colours coming into your crop because the temperature's gone up. You better keep picking fast, otherwise you're going to start to have some reds and you're going to lose your green fruit. From hyperspectral imaging, the early problem detection work, we wanted to test the talk around hyperspectral cameras. There's a number of, I think, world firsts we've achieved. We've developed the first hyperspectral reflectance data for healthy and virus-infected capsicums. And CSIRO have done a wonderful job. They've developed a whole pot scanner, and we're currently working on that to see how that data stacks up. But that's a real big step forward. In terms of next steps, it's about integrating capsicum wrapper yield assessment into automated, accurate prediction of fruit classification. So that allows you to, it's manual to potentially automate harvest by size in the field. It also helps you with yield projections and yield estimation going forward, and potentially helps you with labour requirements. And the next step for the hyperspectral work is to test the capacity to utilise hyperspectral cameras in the field for early disease detection. Because if you probably don't realise, but when you're using cameras for all this work, if your platform shakes and your leaf angle changes, it makes it very interesting to try and interpret the data. Thank you very much. That's all I have, and I'm happy to present on behalf of the DAF team that helped do all this work. Our QUT partner researchers who's done a magnificent job, and our CSIRO partner researchers who've done a magnificent job to pull the work together to date. Thank you very much.
Fantastic. Thanks for that, David. And we've got a few questions come through. I might just get to one of them just in the interest of time with just over 15 minutes left to go. David, you mentioned next steps, taking some of that hyperspectral imagery out into the field. The complexity and time taken to do that, it's within the current project timeframe?
No, it won't be within the current project time frame. Within the current project time frame, we hope to refine and get a real handle on whole plant scanning, because as you'd appreciate, Carl, you've got a leaf, and the leaf growing on the plant is every leaf's at a slightly different angle, so you have to correct for that when you're actually interpreting your hyperspectral reflectance data, because it changes the reflectance. So a long way to go in reality to get it into the field, but we've made some really good basic steps in achieving data and achieving outcomes that haven't been achieved anywhere else to date, in my opinion.
Yeah, great. And just time for one quick one before we move on to Tim, was another question just asking, have you observed differences in imaging data with different light conditions and regions?
Yes, just clouds coming over, and Tim will probably mention this, but yes, light, the uniformity of light at the time of imaging is very important, because but you can correct for it. That's why doing it early in the morning or late in the afternoon, or even at night time under artificial light, is probably the ultimate way to do it. But we ran our trial successfully just after dawn and imaging and late afternoon imaging in field capsicums at Gatton worked quite well.
Great, excellent. Well, thanks very much, David. Again, some great work and a lot of effort behind the scenes, as you mentioned, that aren't always visible on these projects on the face of it. So really great to get some insight there. Now, Tim, I'm just going to hand over to you now and share your screen. So that should be coming up now to bring up your presentation. And Tim's going to be talking to us about some of the work he's been doing with his business called DataFarming and some of the NDVI and satellite imagery. So, Tim, over to you for the last 15 minutes of the session.
Yeah, have you got it up on the screen now?
Yep, we can see your screen and hear you at this end as well.
Yeah, so I'll keep it pretty short, I guess, to stick to the key things. And this is a nice follow-on, I guess, from the other guys of a nice lead into what I'm going to talk about. So I guess, you know, there's sort of some key technologies for horticulture that you've already mentioned, but there's a few others as well. We won't talk about them too much today. There's elevation mapping is a really key thing for waterlogging. You know, you've really got to get drainage under control when you're talking about, you know, managing your farms and landscapes, and it's a really key technology to improve productivity. Most people are probably fairly familiar with electromagnetic mapping for soil constraints. There's been a lot of that done over the years, and it's a very good data set, I guess, to go into your precision irrigation maps and basically location of soil moisture probes and that type of thing. So EM's another good tool. Very great application of lime. We've done quite a bit of work with DAF and other groups across Australia over the time on looking at application, particularly of lime and nutrients in horticulture, with some fantastic results there. Big reductions in lime use based on, you know, applying the right product at the right time in the right place, and so that's been really successful. But all I want to talk about today is basically two things: is the in-crop NDVI imagery and how you can access that, and yield data. They're the two real key factors that we need to focus on, I think, in horticulture, to, you know, we can access right away to get value out of. So I'll just start with in-crop imaging. We've launched a platform that will give you real-time satellite data of your crops. Basically, it's coming over every 2 or 3 days in places like Tasmania. In most places in Australia, it's 5 days. And we're making the data freely available to anyone that wants to use it. And it essentially does what Justin and David talked about already, where you can do NDVI analysis of your farm. You just draw your paddock boundaries in. It will give you access to all the dates, and I'll jump to a live version in a second. And you can get real-time updated NDVI for anywhere in the world, essentially. And like was mentioned before, there's a few things you've got to be aware of, and I'll go through some of those in a minute. But, you know, I'll just jump into cloud. You know, cloud is one of those key things where there's a real limiting factor of satellite data, and this is the real opportunity, I guess, for robotics, is that you put these sensors on the ground and you're doing it in real time. The impact of cloud is quite high. To overcome those things with ground-based sensors, though, you do need a light source. And like you said, you know, there's a real, I guess, problem with light. And if you've got your own light source, you can alleviate some of those problems, like David said. Here's an example of what the impact of cloud has on your NDVI readings from satellite. Is you can see the cloud in red there, where it's definitely picked it up. You can see the cloud shadow, which is this darker area here, and then there's no cloud at all in this bit around there. And if you look over in the NDVI of that paddock, it looks like that there's, you know, sort of poor areas in the field, where in fact that's just cloud and cloud shadow. So it has a huge impact on the reliability of those images, and hence why we've built the tools to actually check for cloud yourself, so that you're comfortable there's nothing over the field when you're actually looking at that data. Because jumping to the next slide here, if, you know, data is just part of the picture, unless you actually put some insight into that data, you're never going to lead to an action. And I think that's a really critical part of what we're doing, is trying to turn the data into real actions on the ground. And so I'll just jump over to the example. Is that come up yet?
So we can see your web browser, Tim.
Yep, you can see the imagery up on the screen. So this is the live version, I guess, running. This is a farm in Tasmania where we've just done we've clicked on the paddock, and we've got the NDVI for that paddock, and you can see the numbers down here, 0.22 to 0.72. So there's quite a big range there, obviously, because a quarter of that centre pivot there is in fallow at the moment. So the bigger the number there, the better the crop, or the more healthy the vegetation is. So we can actually check for cloud on our system. You can see the dates there. They're every 2 to 3 days. The satellite's flying over down there. You can click on the cloud preview, and it will bring up the raw colour imagery to help you assess whether there's any cloud over that paddock or not, and whether you can use that image. So this is designed to work on any web browser. The reason is that we want people to be using this in the field. So it's perfectly built for using on an iPad in the field, and you have tools on the left here to actually locate you in the field, so you can actually use it for in-field crop scouting. And that's the whole purpose, is to get the data in an easy to access format, easy to use, and very low cost. In this case, this part's free, so anyone can use that for free to have a look at any farm anywhere in the world. You just got to draw your paddocks in, and away you go. I guess the key next thing is to turn that into something useful, and that's why we've just released a zoning product, which you can see on the left there, and I'm just going to zone that paddock in real time. So what it's doing is it's going away and looking at that data and creating 3 zones on that field, just to try and get it into a usable format, so that a grower then, or an agronomist can, you can see as we scroll down a bit there, it's automatically picked out those 3 zones. We go and apply different rates to this, for example, and you can then go and immediately export that. Just say there's 100, 200, and 300 kilos you want to put on that paddock. Immediately you can export that as a shape file, which goes straight into the machines for controlling that. So this allows a grower or an agronomist to actually do instant variable rate, essentially, and cutting out all the complicated processes that we've had in the industry in the past. It's been quite a challenge to get people to adopt, because of all the problems with difficult to use, difficult to access data. So I encourage anyone to feel free and jump on and have a look at that, and any feedback is much appreciated. I guess I'll just jump over now to some of the other work that we've just done this year with Hort Innovation and the yield, where we've looked at using the satellite data to predict crop water use. And here I'm showing the graph of basically the crop bulk. We've converted the NDVIs into crop bulk, and basically this is the KC value which you use to determine the crop water use. And what we've done is plot the NDVI derived data, which is in red, the red with the dots, and you can see the literature that's around about what the KC curve should be for any particular point in time on that exact crop. You can see they match very well until towards the end, where there's a bit of a difference, but I think it's a pretty good indicator that we can use satellite data to actually predict crop growth, and this is an actual crop in Tasmania this year. So it's a very, very useful tool. I mean, the next step really is quite simple, just to actually apply that into the software platform and give you real-time crop water use in the field. So there's some exciting stuff we've done this year with Hort Innovation. I just want to finish off on yield monitoring, and this is some work we did a couple of years back with DAF on a project which has now gone to a national project with HIA, looking at yield monitoring. And this is one of the first maps we did in carrots of converting yield data into a profit map. And you know, it was just astounding because, you know, in the past we've never been able to do this. And we're actually monitoring yield down to almost what's per row basis, and I've converted this into a profit map. And you can see here that the blue areas, whilst they are only a fairly small part of the field, are generating between $20,000 and $30,000 gross margins. The green areas are between $10,000 and $20,000 gross margins, and the yellow areas worked out to be between 5 and 10. So overall, the grower probably assumed he did a pretty good job and a reasonable return there. And this is only 1/4, by the way, of 1 centre pivot. So it's quite a small area, but there's a 6-fold variation in profitability. So I think yield monitoring combined with the in-crop satellite imagery are 2 really easy technologies that we can grab hold of today and can deliver huge economic gains and a better understanding of the field. So that's all I've got. Thanks, Carl.
Fantastic. Thanks for that, Tim. And we've raced through that and got a couple of minutes back. So thanks very much for being on point
for you, mate.
Yep. Fantastic. What I might do is just switch out of screens and offer people to send through questions if they've got them. And while we're waiting for those to come through, I might put a question to all our presenters, the panel. We've heard a lot about the ground-based application of in-crop monitoring versus satellite and broader imagery. I mean, what are the main advantages and disadvantages do you see? And feel free to jump in of each of those approaches. Tim, we might start with you. Obviously, what you presented today is available now, but you mentioned that cloud cover and some other factors are still proving challenging for that.
Yeah, and I think resolution's another thing. So, Justin talked about individual plant level. We're talking about 10 megapixels with that free imagery. So I think there's a resolution thing, and then there's the access to the data, and like the ease of process. I mean, I've been playing around with NDVI sensors in horticulture for years, and we've done quite a few with different projects. But I mean, just getting the data off them in a usable format for a grower to make a decision on is bloody difficult. So we've got to start at the basics to get this data in people's hands as a starting point. Otherwise, it won't get adopted.
Yeah, no, they're really good points. Justin, did you have anything to add to Tim's comment?
Yeah, so I guess I agree with that. And the issue with the ground-based robot is just how much area it can then cover. So whereas a satellite can cover a huge amount of area very quickly, the robot's got to drive up and down each row scanning. So I guess it's more applicable to, say, a higher value crop or a crop where it makes more sense to be looking at that really minute detail of each plant and being able to sort of get data about them. I guess the other advantage of a ground-based robot system is that you don't need to just gather that data and then it takes a few days for the farmer to get that analyzed and back to them and be able to do something about it. If the system can sort of take action immediately, you'll be able to do things that you wouldn't be able to do, maybe sort of identify issues and take action straight away before they've done damage to the crop. If you're noticing a pest infestation before it's gone too far, you isolate it to one area and you either send the farmer out to do something straight away, or ideally the robot does something itself straight up. So that's sort of the advantage of the ground-based, but still it can only cover so many hectares per day. So it's that balance of between the two technologies. I think they probably eventually will complement each other, I think.
Yep. And we did have a previous question from Adam just around how much area the Ripper can cover at the moment in a day, or how long it takes to cover, say, 1 hectare, Justin?
It's a little bit hard to say because it depends what kind of operation you're doing. So if you're just doing a scan, we travel at about 5 k's an hour, and again, it'll depend on your row spacing. So, but then if you're doing mechanical weeding, you might have to travel at only 1 or 2 k's an hour at this stage, and spraying. And so it really depends on the application. But I guess to give you an idea of sort of top speed, about 5 k's an hour at this stage for scanning, and then 1 to 2 k's an hour for weeding.
Yeah, great. Excellent. And David, did you have anything else to add to that broader discussion, ground-based versus satellite v imagery, and any comments to build on Tim and Justin there? Oh, sorry, David, we've just got you muted and just unable to hear. Yep, there we go. We've got.
Interesting comments from all the panelists, and I agree with that. I mean, horticulture is about it's a marketing game, and it's a quality game. So what we need in the field and what we need on the ground is information provided back to our growers and our farm managers to help them, make a daily management decision. So anything that can help improve quality or improve yield is just a fantastic tool. That's why something on the ground that can be run after work or during the night and can inform you for the next day, be it for marketing or be it for in-ground farm application of products, is very, very essential to the future going forward.
Fantastic, thanks, David. And Tim, before we finish up, we've just got a quick one from Jono. Just a reminder where we can access that website for your NDVI product.
Yeah, maps.datafarming.com.au.
Fantastic, excellent. Well, look, it's just gone 1:30. We've taken up the hour. It's been a fantastic discussion. I'd like to thank each of our presenters, Justin Clark, David Carey and Tim Neal. That's been excellent. And we've got our fourth and final series this year, webinar in the series on integrated pest management in October, and the details are there up on your screen to register for that. For those that have sent through a couple of questions at the end that we didn't get a chance to get to, we will follow up with you after the session. It's been a great level of discussion, so thanks for your participation, and we'll see you at the next webinar. Thanks, everyone.
Thanks, Carl.
Thank you.
Thank you very much. Thanks all.